In this video, I want to show you how to solve a couple of simple problems in an accelerated frame of reference. So the two frames here are, one, the frame of reference of this person A, who is standing on the ground, and the other frame of reference is that of this person B, who is sitting inside this accelerating vehicle. This vehicle has an acceleration A to the right, and let's say A is equal to 4 meters per second squared, just to take an example. Now inside the vehicle there's a pendulum which hangs at an angle theta, and we usually find this angle theta by solving the problem from the point of view of person A. So in the ground frame, the way we solve the problem is as follows. We draw the free body diagram, tension T and force of gravity mg. And the horizontal component of tension is T sine theta. And since the pendulum is accelerating with the same acceleration as the vehicle, T sine theta is equal to mass of the bob times A. A is the acceleration of the bob, which is the acceleration of the vehicle. And in the vertical direction, we usually write down T cosine theta is equal to mg, because the bob moves horizontally and it has no vertical acceleration. So from this we get tan theta is equal to A by G. So the angle at which it hangs is tan inverse A by G, which in our example tan inverse 4 by 10. This is how we solve the problem usually from the point of view of the observer standing outside. From his point of view, the pendulum is accelerating to the right. Now let's look at the problem from the point of view of observer B. That is, we try to solve the problem in the accelerated frame of reference, the frame of reference which is moving with the vehicle. So from B's point of view, the vehicle is not moving. In fact, the rest of the world is moving backwards with an acceleration of 4 meters per second squared. So how does this person B explain the fact that the pendulum is hanging at an angle? Well, here's what we need to do. When you have an accelerated frame of reference and the frame has an acceleration of 4 meters per second squared, A, to the right, you introduce an extra gravitational field in the opposite direction with the same magnitude, 4 meters per second squared. In other words, apart from gravity, which is the gravity due to Earth, which is 10 meters per second squared, you introduce an extra gravitational field in a direction opposite to the acceleration of the frame. And if this is G, this is A. So in the accelerated frame of reference, the net gravitational field is the vector sum of these two. It points in that direction. Let's find the angle it makes. This angle theta is going to be, check it out, this is A. So we have tan theta is equal to A by G. This is A. So in other words, in the frame of reference of the vehicle, it looks as though there is a gravitational field in this direction. In fact, let me change the wording. I should not say it looks as though there is a gravitational field. In fact, there is a gravitational field in that direction. So what does a poor pendulum do? It simply hangs in the direction of gravity. So it hangs at this angle, and that's how we solve the problem in the vehicle frame of reference. in the accelerated frame of reference. So in this frame, not only do we have a gravitational acceleration which I'll call G prime, which makes an angle of tan inverse A by G with the vertical, we also have from this triangle G prime is square root of G squared plus A squared. So in this frame, the acceleration due to gravity is G prime. So if I now disturb the pendulum so that it oscillates with small oscillations, we can immediately write down the time period is going to be 2 pi root L by G prime. As simple as that. So for our example, this is going to be 10 squared plus 4 squared, and that is square root of 116. So the time period is going to be 2 pi root of length of the pendulum divided by root 116. Imagine solving this problem, that is the time period of oscillation, from the point of view of a person standing outside. From the point of view of the person standing outside, this pendulum is not only oscillating, it's also accelerating to the right. So its motion is quite complicated. Whereas from the point of view of the vehicle, that is in the accelerated frame, it is a simple harmonic motion about a new equilibrium position, and the equilibrium position is tan inverse A by G. Thank you.